What is up, guys? Ryan from elevatecyber here. We're getting right back into this series that we haven't done in a little while. This is the Ethereum smart contract vulnerability series, and we're almost to the end of the list, which is pretty nice here. This is number 14 out of 16 uninitialized storage pointers, and this one, I'm going to be honest with you guys, this is quite a tricky one. It's quite a confusing one to really wrap your head around. But yeah, let's get right into it. We'll explain to the best of our ability, of course. The first thing you need to know is the difference between storage and memory when it comes to Solidity, right? So whenever you store something, a variable or what have you, it will be either stored as storage or memory. And I found this article to be pretty helpful on explaining the difference. So basically what they're saying is, it can be analogous to your computer's hard drive and computer's RAM. So much like RAM, memory in Solidity is a temporary place to store data, whereas storage holds data between function calls. Simple enough, right? So the Solidity smart contract can use any amount of memory during the execution, but once the execution stops, the memory is completely wiped off, right? Makes sense for the next execution, whereas storage will be, it will persist. Each execution of the smart contract has access to data previously stored on the storage area. So depending on what is what the data type is and stuff like that, it will be either in memory or in storage. And so for this contract here, we have a name registrar, public boolean, unlocked, set to false here, and that's just kind of hard coded there. And then you have a struct of name record, and it has a name variable of bytes 32 and a mapped address of address type. And we create a mapping from address to name record, which is public, and we call that registered name record. And then we have another mapping of bytes 32 to address that's public, and the name is resolve for that mapping. And then we have a function called register, takes in underscore name, bytes 32 is the data type of that, and then underscore mapped address is data type address. This is a public function, and we're setting up a new name record here just by doing name record, new record, and then new record.name equals underscore name, new record mapped address underscore mapped address, and then we are resolve, calling the resolve, which was this mapping here, passing in the key of underscore named, setting that equal to the address of underscore mapped address. And then we will be accessing the registered name record mapping that we initialized up here and passing in the key of message.sender and setting that equal to new record. And then we're going to require this is unlocked to run. Well, the problem, right, is that it's hard-coded to false, and it would seem that there's no way to unlock this, thus there's no way to even execute this contract. Now, however, this is where the vulnerability comes into play, right? So, if you know how storage works, and this does get pretty tricky here, really. But state variables are stored sequentially in slots in the order that they appear on the contract. So, in this case, unlocked, right? That's the first thing. That actually exists in slot 0, the 0 index, right? And then registered name record is slot 1, resolve is slot 2, and so on, right, for all of the storage variables. And each of the slots are of byte size 32, right? And there's other complexities that we can ignore, basically. And so, as you might imagine, 0 corresponds to false and 1 corresponds to true. Now, as it so happens, because of the byte sizes of it, you'll have 64 zeros for false and 63 zeros followed by that is followed by a 1 if it's true. So we can use this to actually manipulate this here, turning it from false to true. And it is kind of weird how you go about doing it, but this is what's going on here. So basically, you have to understand that the way structs are handled in Solidity. So it's considered a complex data type, so it goes to storage when initializing them as local variables. Therefore, a new record which the line numbers are off in this article, so I apologize for that. But yeah, new record defaults to storage. So new record here will default to storage. And the vulnerability is caused by the fact that new record is not initialized. So this is actually not properly initialized. And so what happens is it defaults to storage, but it becomes a pointer to storage actually, because it is uninitialized. So because it's uninitialized, it becomes a pointer to the storage, and it becomes a pointer to slot 0. So if you understand a bit about programming, you know, like a pointer can point to an address in memory, and then if you're able to modify what's in that address, then anything that points to that address will also hold that value. So therefore, what you can do is, you know, take advantage of the fact that we know that unlocked is also pointing to slot 0. And so if we can modify that, change the 64 zeros to 63 zeros followed by a 1, we can unlock this contract. And that's exactly what's going on here. And also note that the name record underscore name and the name record map address underscore map address, which are these two lines here, that will even further overwrite some stuff. So changing the storage location of slot 0 to slot 1, which modifies both unlocked and registered name record as well. So we have control of basically both of those variables because they point to that same location in memory. So we can, it can be unlocked, by directly modifying that parameter. So all you would need to do is pass it something like this, and now we're able to use the contract. So we would just enter that in place there. So the preventative techniques for this, right, is Solidity. At the time this was written, which, it is kind of old. I think it was like 2018 or something like that. At the time, the Solidity compiler would throw a warning, and you would just need to pay attention to that warning as a developer so that you did not push this into production if it had this vulnerability. However, as of MIST 0.10, it doesn't even let it be compiled if it has this. And now that was quite a long time ago. If I search Google for this, like this was literally probably somewhere around July 23rd, 2018. So yeah, this is probably not seen too much in the wild anymore. I don't know. If any of you guys know more about this, let me know in the comment section below. I'll see if I can find it in the wild, but yeah, I don't think I've really seen too much about this in the wild either. But honeypots is some real world example, which is pretty interesting. There's basically a bunch of honeypot contracts out there that were deployed to basically hack the hackers, right? Because that's what honeypots are for. And basically it utilized this vulnerability to basically rug the hackers, which is pretty funny. Rug pull them and take their Ethereum. So there's a lot of it was a dangerous space back then in 2018, especially with all these contracts and all these honeypot contracts. I haven't really poked around too much on the Ethereum Block Explorer and stuff looking for contracts. So I don't know if that's still the case or not, but it is pretty interesting to read about this stuff, most certainly. So hopefully you guys are enjoying this series so far. In the next one, we're going to be covering floating points and precision. So yeah, that will be really beneficial to even understand programming in general and how this precision stuff works, because this is a type of vulnerability most likely. I haven't read this part yet, but I would be willing to bet that this might manifest in other programming languages as well, at least to a certain degree. So yeah, we'll definitely go after that in the next one. Yeah, so be sure to subscribe to the channel if you haven't already. Hit the like button as well. It certainly helps me out in the algorithms. And I will see you guys right over on these videos on screen if you want to catch up on this series and gear up with me as we get ready to actually get hands-on with this stuff. Because once we get through this article, these next two sections, we're going to be going out and attacking, doing the basically their equivalent to over the wire hacking CTF challenges. So yeah, we'll be doing that. And I'll see you guys right over in the videos. Thanks for watching.